Today we're talking about finding stationary points and local maximums and minimums. So this is all in your textbook. It says for a function f of x, if f prime of c equals 0. So it's just saying if I find a value that equals 0, then this point is called a stationary point. So theoretically, it's going to be hopefully a maximum or minimum. Not always, but hopefully. It just means the slope is going to be 0 at that point. So what happens on a graph whenever we're dealing with a function, like let's say a quadratic function, it's going to look something like that. This minimum would be the stationary point. And one thing that I said is it's possible that we could have like a third degree polynomial that looks something like this, where right here is the slope of 0, but it's not really a minimum or maximum because the function's going up, it's increasing, and slows down, and it gets to slope of 0, but then it starts increasing again. That's why the textbook uses this wording specifically, that a stationary point is when it has a rate of change of 0, but it doesn't guarantee that it's going to be a minimum or maximum. That's why I use the word hopefully here. Hopefully it's a minimum or maximum. Most of the time it will be, but sometimes it won't be. So what we're going to do today is we're going to try and identify minimums and maximums on these equations, and we're just going to talk more about how derivatives help us identify those points, and then we will prove that they're minimums or maximums. And the way we prove it is box number 2 here. It says if the signs of the derivatives go from negative to positive, there is a minimum point. If the signs of the derivatives go from positive to negative, there's a maximum point. All right. And then a stationary point can be a local maximum or minimum point. Just looking back up here, at a local maximum or minimum point, f prime of x equals 0. So I think we're good with all that information there. So let's start with example 7. Consider the curve s equals 3t cubed plus 2t squared minus 4t plus 2. Find the derivative ds of dt. So I want you guys to go ahead and find the derivative. So do part A, and then on part B we can sketch both of them, but why don't you go and do part A first and take a minute to work on that derivative. Let's try and sketch this function on our graph. And it looks like we can probably just do a scale of 1 for the x's, 1 for the y's. I mean, it looks like we're pretty good there. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And I'll share with my screen in just a second here. All right, back to our iPad screen, which is working again. Yay. All right, so I'll go and do the function in blue here. And it doesn't need to be the most accurate function. I do know that the maximum is going to be just below -1. And it's going to be at like 5. So something like that. Then the minimum is going to be at 0.4. Somewhere down here. And then it's going to take off again. So that's the first function. The derivative function, I'll do in red, is just a quadratic. And it's just going to come in, cross the x-axis at the same point as the other one, turn around, cross the x-axis at the same point as the other one, and get back out of here. So that's what the derivative is going to look like. All right, something like that. That's how we would do just a quick sketch. Now this part C here says solve the derivative equals 0. So basically we take our derivative, 9t squared plus 4t minus 4 equals 0. And now we can go ahead and use quadratic equation to solve. We could use completing the square to solve. So we could use a lot of different things like that. Or we could be really smart and just use our graphing calculator to solve. Or Desmos, which we already did. So we know that t is going to be equal to negative 0.925. That was one of the values. And the other one was 0.481. All right, so when it says say solve here, we could just use our calculator. So that's what I'm going to put here, use calculator. Okay, that's it. And then this part I don't love, part D. It says state the feature of S indicated by these points. So it just means, what's happening at these points. What's happening when the derivative equals 0? And you would say that like there's a local maximum and there's a local minimum. That's what's happening at these points. And we can tell by looking at it graphically again. There's going to be a maximum and a minimum. So we can say local maximum at t equals negative 0.925. And then there was a local minimum at t equals 0.481. That's what part D is asking of us there. Okay, there was a maximum and a minimum. All right. It's just kind of a weird problem. I don't love the way it's worded because it was just as indicated by these points. Like, what points? And then last part E says if the domain of a function is restricted. So now we just want to look at the viewing window from -2 to +2. Find the act. Okay, so let me go back to our screen now. I've got screen. Having technical difficulties today. So we said the minimum value, just by looking at Desmos, the minimum was -6. And you got to be careful because I fell for it myself. I was looking at the wrong one at first. And the maximum is at 26. So you got to make sure you're looking at the appropriate graph when you're looking for those minimum and maximum values. All right, absolute mins, absolute maxes. All right. For example 8, this one's going to ask us to find a derivative and then sketch the curve. And the curve we want to sketch, we just need to sketch the original x or 1 plus x, where you can just graph it and sketch it. And then find the coordinates of any local maximum or minimum points. So local being the keyword. So we're looking for any turning points. All right. So what I want you guys to do is let's try parts A, B, and C. You should be able to get those 3 parts done right now on your graph. So look for local maximum minimum points and find the derivative. Don't forget to, when you're looking for the derivative, to rewrite 1 over x as x to the -1 power. That's the hint I can give you for that one. So again, I said just easiest way to do it is rewrite it as 1x plus x to the -1, just so that when we're taking the derivative of it, we can say y prime is 1 times x to the 0 power plus -1 times x to the -2 power. So this really becomes, dy dx becomes 1 minus, and then we could say 1 over x squared. Or we can say 1 minus x to the -2 power. But when we're graphing it, I think it's going to be easier to graph it in this way. All right. Then we should be able to go ahead and sketch a quick graph of our function. And for this one, the original function, it's going to be coming up, and it's going to take a sharp turn and head down, and it's going to be coming from up here, sharp turn and head out. So there are indeed a local maximum and local minimum value that we can find. And my sketch might not be the most accurate, but that's fine. We were just doing a quick sketch. Local maximum happens right here. That's at -1, -2. Local minimum is at 1, 2 on the other side. All right. So we can identify the local maximum and the local minimum. Now, part D, this is the other important part here. It says find the gradient of 2 points close to but on either side of the minimum point. So we'll just recap. The minimum was 1, 2. And this is the part where we're proving that it is indeed a minimum without using the graph. So we can tell, hey, that's clearly a minimum on the graph. The way we prove it comes back up to our notes here. It says, if the sign of the derivative goes from negative to positive, there is a minimum point. So we're looking at the slope of the y values of the derivatives. And we pick points that are really close to 1, 2. So like I can say, we can pick any point we want. The only rules are it's got to be on each side of the point 1, 2, and it's got to be on the same continuous segment. So for example, what I mean by that is I've got the point 1, 2 right there. If I picked like -1/2, that's going to be on the other segment. So I got to pick something that's on this continuous segment. That's what I mean on something to the left of it. All right. So let's go ahead and pick x equals 0.5. All right, so 1/2 for x. And we're going to plug that into the derivative function. So f prime of 0.5 equals 1 minus 1 over 1/2, or 0.5. And we just throw that into our calculator and we'll get a y value. Which becomes 1 minus 4, oh, it's 1/2 squared. There we go. 1 minus 4, so it becomes -3. So 0.5 comma -3. That's for the derivative. So obviously the 0.5 comma -3 is not going to match up with this graph up here. But that's telling us, hey, we have a negative slope, which does check out. This is a negative slope on the left side of the graph. And then we do it again. Let's do f prime, and we'll pick something on the other side, 1.5 this time. And we're just going on the right side of 1 and 2, somewhere over here. 1 minus 1.5 squared. This time we're going to get like a 0.44 or something. But we end up getting a 0.556, so a positive value here. So we have a negative value and a positive value. And that right there verifies that we are indeed, that right there verifies that the slope is changing. It was a negative slope before that point, and now it's a positive slope after that point. And that's kind of what we would talk about for the last part. Explain why this shows the point found is a local minimum. And remember, you can pick any points you want that are to the left and right of 1, 2. I just chose 1/2 and 3/2. So you could have had different points than me, which is perfectly fine. Okay. So explain why this shows that the point found is local minimum. We would say the slope changes. We can say the derivative has opposite signs. Meaning the slope changes. All right, that's the idea for example 8 there. And that's really the key for today is, can you identify if the slope's changing? There could be an IB question that asks something about that. Hey, you can see graphically that the slope's changing. Can you prove it to me algebraically? All right, and that's just where the derivative comes in handy and says, hey, that's when the derivative comes from a positive value to a negative value. It crosses the x-axis. That's the idea for example 8. Any questions so far on example 7 or 8 today? Hopefully we're feeling okay.
Could you move over the screen a little bit?
Move over like that? Bam. Yeah, sorry. Trying to stay zoomed in enough so you can read it. All right, let's go ahead and look at the last problem here, example number 9. This is a good real world problem. I'll read it right now while you guys are working on this part. It says a can of dog food contains 500 centimeters cubed of food. The manufacturer wants to receive the maximum profits by making sure that the surface area of the can has optimal dimensions. Let the radius of the can be r centimeters and the height h centimeters. Find the dimensions of the can that will have the minimum surface area. So they're trying to keep the volume of 500 centimeters cubed, but they're trying to find the smallest possible surface area so that way they use fewer materials when they're making their cans. That's the idea here. All right, so for this example here, we got to know 2 equations. We got to know a cylinder. We got to know volume of a cylinder, which this stuff is given to us on the IB exam. All right, so it would be in your formula booklet. Volume is pi r squared h. So remember, a cylinder is a circle, so the area of a circle, and then times the height. That's where volume comes from. And in this case, the volume is 500. The other thing we need to know is surface area. Surface area is going to be 2 pi r h plus 2 pi r squared. I don't expect you to remember that. That is given to you on the formula booklet. But what we want to do is we want to put these equations, they both have h's in them. So we want to go ahead and solve for h and then write one equation for them. That's the idea for this problem. So, for example, I can say pi r squared h equals 500. That's the volume equation. And I can just divide everything by pi r squared. And I get h equals 500 pi r squared. I could solve for r as well and put everything in terms of h, but it's going to be a lot easier to deal with just this one h rather than subbing in for an r here and an r there. So what happens on the other equation now? The surface area is 2 pi r, and then I'm going to plug in for h, 500 over pi r squared plus 2 pi r squared. And I can go ahead and simplify. 2 times 500 is 1,000. The pi's divide out, and I'm going to be left with an r in the denominator of a fraction. Oops. So now I have an equation for surface area in terms of radius only. So that's going to be nice. Now I only have one variable that I'm worried about, just the radius of the can. All right. For these ones, we're looking for maximums and minimums. This time we're looking for the minimum surface area. So we could go ahead and graph this equation in terms of x's, like y equals 1,000 over x plus 2 pi x squared. And that's going to hopefully find the minimum value. The other thing we could do is we could take the derivative right now and say, let's find ds over dr, the derivative of the surface area with respect to r. And that should be a capital S, not a lowercase s, so I didn't do that well. Let's do it in a different color too. ds, capital S, dr, lowercase r. And I could say this is 1,000 over r, that's like 1,000 r to the negative 1. So that'd be negative 1,000 r to the negative 2 plus 2 times 2 pi r to the first. So this really becomes negative 1,000 over r squared plus 4 pi r. That would be the derivative of this equation. All right. And again, I'm finding the derivative because if I can find the y values when the derivative equals 0, that's going to give me the maximum and minimum points. So that locates the maximum values of the original function s. All right, that's the whole reason we find derivatives. Okay, so that's the idea for this particular problem. Now we could, we could graph it. We're gonna mess with our viewing window quite a bit because this is a very big scale problem. So we would have to mess with the viewing window a little bit. I think the x's are gonna be pretty small, like -5 to 5, but the y's are gonna need to go like way up into the hundreds or thousands. All right, but that's the idea for this particular problem. Now, do we want to look at this one on a graph? We could graph it and take a look at it together. And maybe that'll help us a little bit. Let's see if I can graph this real quickly. The original equation was 1,000 over x plus 2 pi x squared. So we'll go ahead and we can say we want to look for the point specifically because we can't do it with the original equation, but with the derivative we can plug in and say we want to look for negative 1,000 over x or over r plus 4 pi r squared or 4 pi r equals 0. And plug that into our calculator, and we're going to find out that r equals 4.301. All right, or plug that into our graph. But we need to be able to show this setup of this equation. If it's on an IB exam, we got to show this setup right here. Hey, I know I need to set that derivative equal to 0. That's going to help me find the r value. That gives me the minimum. All right, and now once I have that minimum value, I can plug that back in and solve for y, which will give me the surface area answer, the 348. Okay. Oops, sorry, I'm on the wrong screen, aren't I? But let's go back to the iPad. So, so what I was saying was you have this right here. You got to be able to draw that equation, 0 equals negative 1,000 over r plus 4 pi r. And then you can just go ahead and find your answer and say, okay, that's it right there. That's the radius I need. Okay, and it did ask us to find the radius. Okay, it says the manufacturer wants to receive this. Let the radius of the can be r. Find the dimensions of the can. So we found the radius. Now I want to find the height. So I can go back once the radius is found to my original equation here and plug in. H equals, what is it, 500 over pi and then 4.301 squared. and then I'll find my h, and h should be like 8.6, and we'll just round to the nearest tenth. That's fine. So that's how I find the height at the very end of the problem. But I'm using the derivative because the derivative is going to help me algebraically set up and solve. If you were in a regular calculus class, you'd be expected to solve this equation for 0. But thankfully, we don't need to solve it. We can look at the graph and say, hey, here's the point. That's what I need to do. All right. And then I have one more note here that was just from your textbook. It just says, if a function to be optimized has only one variable, then either a graphing calculator or differentiation can be used directly to find the maximum or minimum point. So that's why we find one variable first. So if we find that one variable, now we can find that maximum or minimum point a lot easier by graphing. So the hardest part about this question is really getting it set up to be solved for one variable. All right. So your assignments now.